Okay, thank you. Thank you for EBPO for inviting me, and it's a pleasure to present the work of on breeding in banana. And while you see in the background of every slide IITA, I need to stress it's not an IITA activity only. We are working with a lot of partners, and if I, in a nutshell, if I talk about East and West Africa together, we work with about 30 different partners. But two of the key partners are today also on the cafe, and they will present after my presentation. So at IITA, we are breeding plantains in Western Central Africa. These are triploids, that's why you see AAB. In the middle, you see the Highland cooking bananas, AAA, and then we have the mchare bananas, AA. So we are breeding diploids and triploids. And why are we doing that? Because the yields are rather low. If you see that the potential yield is 70 tons per hectare per year, and farmers reach only about 50, sometimes 30 tons, and then they need to replant after 2 cycles, then we see there's an issue. Another reason why we are breeding it is simply because those bananas are very important. You can see that for the plantains, 12.4 million metric tons of plantain are being produced in Western Central Africa. The Highland cooking bananas, 9.8, so roughly 10 million metric tons. And that there are 3.2 million farming households in Africa depend on plantain, and 2.5 million farming households on Highland cooking bananas. So roughly speaking, 7 million farming households depend on bananas and plantain in Africa. And the plantains in Africa are ranging from Eastern Congo up to Liberia, so encompassed by the red circle. And you can see on the left side the plantain. The top one is so-called French plantain. And here you see the French plantain. On the other side, you see the Falson plantain. And Africa is a center of diversity of plantain. There are about 120 different plantain varieties. And Africa produces about half of the plantain in the world. A little bit in India, and all the rest is in Latin America. What else do we have here in, I'm trying to move to the next slide. What's happening? It's blocked. I'm trying to move on.
Maybe use the arrow.
Okay.
It's fine.
So, okay. So the yellow mark shows the highlands of East Africa. So around the Great Lakes, and here you have Lake Victoria in Eastern Africa, basically the lake which is bordering to Uganda. And in that yellow zone, matokes are extremely important. So these are bananas which are happy above 1,200 meters above sea level, up to about 1,800 meters above sea level. And important in Kenya, Uganda, Rwanda, Burundi, Eastern Congo, and Northern Tanzania. And in the green circle, we have the so-called mchare bananas. These are diploids, but these are huge, they produce big bunches. And these are important bananas, again, as a staple food crop. They all need to be processed. All the bananas you see here today are cooked or boiled or fried. They are rarely being consumed raw. Now, where do we breed with IITA? Either alone or in partnership. We are breeding in Nigeria in 2 locations, and this is the Plantain breeding program. And then look at the graph in blue. So in areas of a high rainfall conditions, high humidity, and in the lowlands. And then on the right, we are breeding together with NARS. No, things are going too fast. And where we are breeding under B model conditions, and in Tanzania, we are breeding under very dry conditions. So we are basically breeding in the center of origin of the bananas. And I forgot to mention, for the matokes on the top right, there are about 70 different types of matoke banana varieties. And now let's go straight away to end products. So pita, which means plantain made from IITA, has been registered and accepted in Ivory Coast, 2016. It's now being grown in Togo, in Benin, in Mali, Burkina Faso. It's been planted out in Sierra Leone. So breeding is possible. I come back to that point. And the same thing happens here. This is the result of the work between NARO and IATA about developing the cooking bananas. On the left side, you see the original landrace, and on the right side, you see the hybrid, which is has been selected and tested in different environments. Okay, so cooking bananas are also being developed. So it's possible. Now I want you to explain how we are doing it. So breeding basically goes over 8 steps. So you start with step number 0, you go to number 1, 2, 3, and so on. And I'm going to guide you through all those different steps as part of the breeding program. So let's start with the first one. The first one is basically with people and people and people and people to say, what do we want? Basically, what is needed that a new hybrid will be accepted by the farmers and the consumers. This can be, in the most extreme case, the same variety with one extra trait, for example, nematode resistance, or it can be the same variety with a few extra traits. This is so important, this work, that it should not be in the hands of the breeder. And that's what we are developing, a product profile with many partners, and that means the national programs, the consumers, the traders, the business people, etc., etc. And they say what is needed to make it. And on the left side, you see here a kind of a table. I'm not going to guide you through all the points, but the point is that we are qualifying some of the traits with number 1. It means must have. Number 2 means that's interesting to have, and number 3 is a trait that's simply a bonus. So the new hybrids have at least to have something superior for the traits which are marked number 1. And this is in fact our guidance. What is not in this product profile, we will not tackle. If somebody comes with saying, you should breed for that, and it's not decided by the people, we will not do it. And then we have been able to develop yield increases with up to 1.4% annual yield increase for matoke bananas and for plantain with 2.5%. To put this in perspective, the CGIAR, so IITA, Biodiversity, CIAT, IRI, they've set a target that all breeding programs have to develop hybrids at the pace of around 1%. So with the bananas, which are, and I'm coming to that, which are sterile, we're able to go above the targets. We published it a week ago. So on the downside in the Vitica, you see that we are able to get genetic gain and having the data to prove that we are going for 1.4%. And the other publication, 2019, show it in Plantain, we can go even to 2.5%. So let's go now to the step number 2, or basically stage number 1, trait discovery. We call it pre-breeding. So basically preparing the breeding program for crosses. And an important thing in pre-breeding is basically that all the germplasm needs to be phenotyped. So down on the left for nematodes, for weevils, that's an insect. For fungal diseases, which is black sigatoka, affecting the leaves, or the roots, which is called fusarium. And then on the right side, a bacterium. So we are phenotyping all this one because you need to know the source of resistance. The other one is developing molecular traits. This is just an QTL map for banana weevils. So we're developing maps and for weevils and for sigatoka and for fusarium and so on, so that we can develop, so with this QTL information, can develop basically molecular markers. We are looking for the genes for fruit diameter, because in the end, when we cross bananas, we need one with fruits. And if we make crosses, we also have sometimes hybrids without good fruits. And so we are already landed on chromosome number 3 and rather close to the gene, we think. And then we need to know about genetics. So we need basically make crosses and be able to propose what's going to be the outcome. And therefore we're doing genetic studies for different traits. This is just a publication about what we're saying about fusarium. So in pre-breeding, we need to do phenotyping. We have to develop the molecular tools. And we also have to develop the metabolomic tools. So this is the work with colleagues in UK and about, let's call it taste. So we're doing metabolomic studies on what fruit quality, but the same thing, we're doing the work on the vitamin A. So we found varieties which are very rich in vitamin A, and also on the enzymes, the proteins, which are able to break down starch into sugar or not breaking it down. And that's important when we are developing a new variety. It has to be starchy, so we need to know what's also going on that level. So we combine all those tools in preparing an efficient breeding program. And now we go to stage number 2. We want to develop parents. So parents which can be used, I would almost say à la carte, to develop something we want to have. And that means in this complicated breeding program that we focus on different levels. So you see here in the red circle in the middle, tetraploids, that's one group of parents. On the right side, you see diploids, that's another group of parents. And basically, if you are able to do diploid improvement program and a tetraploid improvement program, then you are much faster able to design triploids and look down at the picture. And this is in fact our end product. Of course, we're not able to do everything, and I'm happy that Jerome is here because it's together with him and his team that we are going through this whole different steps of the breeding program. Now, looking at the work further, when we have produced seeds, and that's quite a story to get seeds in a sterile banana plant. And here I want to give you an idea. So in 1 year, we produced 25,000 seeds. Look at the red arrow. We have to germinate them in vitro. So on the top left, look at it. We cut open the seeds, then we extract the embryo, and then we allow it to germinate. Look at the right side. And from the 25,000 seeds, only 62% will have an embryo. And of those 62%, only 4%, 3.8% will germinate. That means that we will obtain 800 hybrids, more or less, from 6.5 hectares. Now, if you compare it with another breeding program in rice or maize, you see that we are really not that fortunate with the banana plant. But anyway, I showed you already previously, we have hybrids and that we have a very high genetic gain. So we are delivering what is expected. Now, here, our screenhouse in Uganda full of hybrids. And I'm sure that Maro can show the same kind of pictures. And I'm not going to give you all the details, but the point is quite simple. You see here high numbers. You see 2,600 hybrids from something, 170,000 hybrids, etc., etc. Selections going on. In the end, we have 264 material hybrids being selected for multolocational trial and so on. So banana breeding is viable and can be done. And then whenever we've developed something, we need to test it whether it still has maintained resistance. On the right side, a variety, a hybrid, which is still susceptible to the banana weevil. On the left side, resistant to the banana weevil. And here, on the left side, you see hybrids which are Fusarium resistant. And on the right side, in the red circles, hybrids which are Fusarium susceptible. Now, when we are breeding, it's a complicated process. You have to cross triploids with diploids. They're not all flowering at the same time. We have to make decisions all the time. That's why every plant has a barcode. And our teams are scanning the barcodes, and then they know what to do with that plant when the plant is flowering. And then the field book will give us information, say what data needs to be collected. And once a plant has a code, it means the bunch gets a code, the seeds will get a code. When we work in vitro, we have codes. When we germinate, when we multiply, the whole process is documented by barcoding, and in real time, everything comes into a database. So basically, from anywhere in the world, we know what's going on. And apart from following what's going on, we do quality checks. So use a fingerprinting technique. And to be sure that we are not mixing up varieties or hybrids, we regularly do some fingerprinting to say, hey, there's no mix-up, you can keep on going. And all those data enter into the so-called MUSA base. And the MUSA base provides the real data about pollinations, about seed germination, about phenotyping, a pictorial guide, but also provides us information what statistical design we have to apply and what should be the field layout so that we can immediately analyze the data. So it's basically integrating all the operations, and this is open access. Now, I've guided you from stage 0 to number 4, and let's now turn this into a pictorial guide. On the left side, you see the original matoke, the original variety, and this was crossed with a diploid. Look at the blue line here, and that cross resulted in a tetraploid. And then we are doing diploid improvement. So the bunch in the middle, that's very small bunch, that diploid, we crossed and crossed and crossed again, and we were able to improve it to another diploid. And you see how big that bunch is. And it's that crossing of diploids among diploids because stage 2. And then we cross that with the tetraploid to end up with the triploid, which you find here on as an end product. And then we go for multilocational testing. That's stage 5. And in our work, it's done in the central Uganda, in an area where I would say, roughly speaking, the soils are not so good. It's done in southern Uganda, where it's a drier zone. It's tested in Tanzania, where we have a complete different agro system. It's tested in Tanzania under volcanic soils, and then in the end, near Malawi, where it's rather cold. The results of 5 years testing of those hybrids, in the end, results into the identification of varieties which can go to the farmers. And this is done by national programs. And Mary will talk about that later, but that is out of the hands of the breeders. Then the hybrids which have been selected will be released by the national authorities. And I'm happy to show you here that in July of this year, the Tanzanian government released the products from the narrow ITA breeding program for the farmers in Tanzania. With the plantains, we are all over in farmers' field already since long time in Nigeria and Cameroon, and we are sending our material all over the world. We are now in more than 16 countries, and very importantly, I show you India, because in India we have race 4 of Panama, which we don't have in Africa except in Mozambique, and so there the Indian colleagues are testing our material for resistance to race 4. So in different countries, and to conclude, I want to say the following. It has been said for such a long time, banana breeding is hampered by long generation times. You need 2 cycles before you have data. By triploidy and sterility, that's why you are not moving fast. I can tell you from the collaboration we are having with national programs in West Africa and in Uganda and in East Africa, especially narrow, that we have a lot of hybrids. I would say basically the pipeline is open to release on a regular basis more hybrids in the future. So breeding is possible, but it can only be done if it's part of a multi-partner collaboration. For sensory, for product profiling, for testing, etc., etc. And that's why I'm happy that with the closing of my talk, in fact, the Banana Cafe is not closing, because now I would say it's good that we can have the presentations of Mary Mwanga and Jerome Kuberiba to complete the full story. I thank you for your attention.